Hello, my name is Jonathan Len, and this is a presentation for my cloud computing final project. This is about a serverless Convex Hull web application. So you might ask, why a Convex Hull web app, or what is a Convex Hull? Uh, but in general, what it is a pretty common algorithm in computational geometry, and we can use it to calculate bounding boxes, which may be useful for computer vision, or we might be able to use it in some math problems to find the convex approximation for problems to simplify them. Uh, Originally, I had planned to implement this in a high performance compute kind of fashion, so try to get good performance by like parallelizing and optimizing this algorithm and using the scalability that the cloud offers. But you'll see how that proved to be too difficult in the next few slides. So I decided to switch away from that. Um, in terms of serverless, so I'm making a serverless web app as opposed to a traditional server-based one because serverless cloud computing, I mean, a lot of what we've learned in this class is that these new cloud models offer like really competitive pricing to traditional servers. In particular, stuff like lambdas, which are you only need to pay for the amount of time that it spends computing. Um, and a lot of web servers just have to respond to requests every now and then. These are scalable, and you only pay for the amount of time that you need. So it's very competitive in that respect. And also, it offers a lot of benefits with scalability. Scalability and maintainability because all the services are decoupled from one another. So I mentioned that I wanted to start with the high performance compute, and this was just because it's more similar to our first project. But I think in the end, uh, trying to implement the quick hull algorithm, which is an implementation of convex hull, was just too difficult because of all the little details in computational geometry. So I ended up just trying to create a web app using an existing 3D quick hull library and just see how I could use different AWS serverless technologies to make it useful. So a brief introduction to quick hull again. Um, I mentioned earlier that it's like a bounding box. So it's the smallest convex hull which contains a set of points. So given a set of points in 2D, you can think of it as putting a rubber band around those points, and that rubber band is your convex hull. In 3D, you can think of it as shrink wrapping your set of points, as this rabbit is currently. The gray lines represent the convex hull. And there are a lot of cool geometric or mathematical properties that I probably don't know and are very interesting, but yeah. So, but the problem was that even though it's a really cool algorithm, so this quick hull is a divide and conquer algorithm, and uh, but the problem is to be able to implement it well, as in robustly handling the degenerate cases, handling all the problems with bad topology when you create new faces or merge faces, and also just the basics even of the procedure, having to store the data structures, like for example the half-edge data structure, as well as performing all the necessary steps of the algorithm, like a DFS, to find all the visible faces from a given point. It's a little difficult, or there's a lot of intricacies. So I think given the scope of this project and being focused on the cloud computing project, I couldn't implement it, and definitely I couldn't optimize it like in the time given. So saying that, I will say that I looked at these three resources for Convex Hull, or Quick Hull in particular, and they're very good. This first one is a slideshow given by Dirk Gregorius from Valve Software, and it explains very well about a lot of the intricacies of 3D Quick Hull. It's over 100 slides long, but it's really great. The third one is implementation in Java, which I would say is pretty academic, so it's like not too hard to understand and read. And I tried to follow that very closely, but I only got up to this, creating the initial simplex, which is not very far in the algorithm. Um, and then the center one is a common implementation of quick hull called QHull. So in the end, I ended up using, because I was using Go, an implementation by Marcus Wall called Quick Hull Go, which is a 3D quick hull implementation. So what would this look like in the end? So if it's a web app, I was thinking maybe users would be able to simply upload a file, maybe view their file in 3D, and then view their quick hull or convex hull version, shrink wrapped version. That's basically all it would need to do. Similar to like this very popular, or this website that I use often called Optimizilla. You simply go there and you can upload a file, and it'll do a simple transformation on it, which is compressing the file. In terms of my tech stack, this is what I used on the for building everything. I used AWS CLI, so this handled all the AWS requests, and I use makefiles rather than bare shell scripts because I'm just more accustomed to them and their macros. For the lambdas or the backend, which calculates the convex hull as well as does other backend stuff like pre-signing S3 requests. This was done using Golang and the following packages listed there. And for the front end, I used Vue.js because it's simple. It's a simple framework, and I liked it. For 3D rendering, I used 3JS, and I also use the Vite framework for Vue because it just helps accelerate the testing and the deployment of Vue app. Here's my architecture diagram, which is a little larger than it should be because I only implemented stuff on the right of this dotted line here. So yeah, I'm gonna go through the whole thing because I was planning to go through more of this, but some unexpected setbacks caused me only to be able to implement this much, which is enough to have a working version of the app. So, but I'll still go over the entire thing. So you can think of this part on the left as a to do in the future, and I experimented with a lot of it, like Cognito and RDS, but I wasn't able to experiment with all of it. So we can start here with S3. So S3 is the basis of our application. We're gonna have a front end hosted on just by a regular S3 bucket and using the S3 static hosting capability. And we have a second bucket to host to store the files that will be storing the 3D models, the .obj files. So I use obj files because it's a very simple file format for 3D files. And so the website bucket is public, just statically hosted, versus the uploads bucket is not public by default, but the lambdas have access to it and they can grant access to other to outsiders by pre-signing the request. And we'll get to pre-signing in a moment. So then the website can access the API gateway, or actually anyone from the outside can access the API gateway, but we need a course header set up so that the website can access it as well, or course policy. And the existing API endpoints currently are pre-sign, which allow us to get a URL to access an object in the uploads bucket, and the convex hull endpoint, which does exactly what you think it would do. It calculates the convex hull of an object that's in the bucket, in the uploads bucket. So again, what pre-signing means is if we want to access or put, so if we want to get or put an object into the uploads bucket, we need a special URL to do so. And so if we want to put one, we have to make a request to the pre-sign, which gives us a put request, a put URL, and then we can put to that put URL, which will put the create an object in the uploads bucket. And similarly, if we wanted to get a get URL, we would do the same thing. We would send a request to the pre-sign endpoint, which would send a request to the pre-sign lambda, which would get a get URL and return it to you. Then the second endpoint is the convex hull. And what this takes as arguments is simply the key of one of the models in the uploads bucket. And it'll return the key of the new model it'll create, that is the convex hull of the previous model. And the way it does that is the convex hull lambda also has access to the uploads bucket via lambda execution role. And it creates a new object and puts it in there. So that's basically everything that's already exists. I don't have to talk about CloudWatch or IAM too much. The IAM is just to set up the necessary permissions for the Lambda, and the CloudWatch is used for debugging to set up logs for the API and a gateway as well as the Lambdas. For things that I would like to implement, we can continue talking about this. I didn't get to experiment too much with Route 53 or Cloudfront, and these are used to help deliver your website to the internet. So Route 53 in particular is just for DNS, because the website bucket doesn't have a custom domain name, or it's like a subdomain of whatever static hosting AWS has. But if you want a custom domain name, you have to register it through some domain provider, and you can use Route 53. And then Cloudfront is used as a CDN to help accelerate your delivery to the internet in general for the bucket contents or for API gateway or even the uploads bucket stuff. We also need Cloudfront to handle HTTPS if you want a secure application. And one of the things I wanted to do was to use Cognito to manage users. And Cognito also requires HTTPS, so that's why I have a link here with Cloudfront. But Cognito would also allow for a lot of other interesting features. So not only would you be able to have your users store your models that you uploaded, but you can also create a authorization for the API gateway. So every time you send a request to the API gateway, you have to authorize yourself, so it knows who the user is. And so this might require another Lambda to manage the authorization to verify the tokens. So that would add some extra complexity that I didn't have time to finish implementing. Another thing I wanted to try was to create a database to be able to store these models and maybe add some extra information there, such as like who's the user, maybe is this the convex hull of another model, and so on. So this would create some extra gateways, such as, for example, list models, if you want to list all your models, and some extra lambda, such as being able to list the models or create a new model, which will update the database or read from the database. And of course, this will also have to update the lambda execution role, and so on. Yeah. So that's the entire architecture diagram. This is just a review of what I was just saying. And I think I can go through this pretty quickly because, again, it's a review. On the front end, we have Vue and Vite as a build tool, 3JS as a library for displaying 3D files, and static hosting. The API, we just need to set up the CORS policy as well as the necessary endpoints and stages for AWS API gateway. The backend are a series currently of only 2 lambdas, which are just Go programs. I use the Marcus Waugh Quick Hull Go library and the AWS SDK and implement lambda proxy integration. On the backend, I use Makefile and AWS CLI v2. And the buckets, I have 2 buckets. One of them has the uploads bucket has public access via get input requests, and the other bucket for the website has static public web hosting. And the things on the left, again, that I couldn't implement are the Cognito user pools, which would allow for a lot of cool things like OAuth and authorization of API endpoints. But the problem was that it requires HTTPS, which we couldn't do because of AWS Educate didn't allow it. There's also RDS, which I just didn't have time to implement, and then Route 53 and Cloudfront, which would allow for more delivery or better delivery options like DNS, HTTPS, and CN. just to show a general idea of what the build process looks like, here is the example from the top level makefile. So you can look at these targets and see like there are a lot of sub targets within each of these, but basically what this encompasses is building the website, the front end, the Vue app, and then building the Lambda, which is like a Go build, and then calling a bunch of AWS CLI commands. So that's the entire architecture. Now I'm going to show a demo. I have it pulled up here. And it's a very simple application. You can see I didn't put any effort into styling it. But what I'm going to do is choose file to upload. So let's look at a cow. So I took this from the MIT graphics website, and you can see that here, if I zoom in a little bit, it's very clearly a cow 3D model. And if I calculate the convex hull of it, it'll take a moment, but the lambda is calculating, and then you can see this resulting thing is the shrink wrapped version of the cow. So it's a little hard to see here, so what I'm going to do is download it and then upload it to this other 3D viewer. And maybe this is a little bit easier to see that this is the shrink wrapped version of cow. Or I'll do another example. Let's take a teddy bear. Yeah, so this is teddy bear, and do the same thing, calculate the convex hull. Yeah, and you can see here that, well, it's hard to see again here, so let's download it again, just view it here. Yeah, and you can see here's the tail, here are the ears and the arms. So that's the teddy bear. So that's all for the demo. So I learned from this because I spent a lot of time trying to hook up all the components correctly, but in the future, if I wanted to actually build a web app and be more efficient, then it would be better to use Amplify, because this has a lot of integrations with other apps such as Cognito and Route 53 and Cloudfront that I didn't have time to implement. And also because the makefiles were cool. I mean, I love makefiles, but they're unwieldy. So using the CDK will allow you to have full like general purpose language programming language logic. So that would probably make it more efficient as well. So that's all. Thank you for watching, and the source code is available on GitHub.